Okay, then, good morning, everyone. Good morning once again. Any questions or queries before we start? The class, as I told you at the start of the year, the class test in this unit is in the last week. If you look in the link at the top, the basic information. The unit, the assessment takes place with 2 class tests, the first of which is in the final week. So where are we now? We're in week 7 now. So that's week 12. So it's coming up in a few weeks. Very soon I will put up an example or 2 of mock tests or previous class tests, just so you can see it, and get an idea, familiarize yourself with the kind of thing it's going to be. But we'll give you more information about it closer to the time. Okay. But the mock test or previous test, I'll put that up soon so people can start to see what you're in for in the last week. Okay. But certainly don't go leaving for Christmas early. There's class tests taking place in the last week of term. Okay. So we're in this section 2.5 on convergence tests. And we've got one major test left to do called the ratio test, and then one little one called the root test in Theorem 2.10, which I won't make much about. So before we look at the ratio test, it's related to the geometric series test. So I just want to remind you about the geometric series test. So here we had a series sum of xn n equals 1 to infinity, where the form of xn was always ar to the n minus 1. Some numbers a and r, so this series looks like a is the first term, then a times r is the second term, then ar squared, then ar cubed, etc., etc., etc. Okay, so each term is generated by multiplying the previous one by a. Of course, you can factor a out of everything. So really, whether or not these things converge depends on the value of r and whether or not that series in the bracket converges, 1 plus r squared, etc. Now, we analyzed this and we found this converges. Okay, we'll assume a is non-zero, because otherwise it's just a whole load of zeros. This converges if and only if the value r is strictly less than 1. The absolute value of is strictly less than 1. Okay. If it was greater than or equal to 1, then the series diverged in the a not equal to 0 case. Okay. Now notice r is called a common ratio. You take one of the terms xn divided by take one of the terms xn plus 1 divided by the previous term, then you always get the quantity r. Yeah? Because you're taking ar to the n divided by ar to the n minus 1. Okay? So r is sometimes called a common ratio, because r is the ratio between one term of the series and the previous term. Okay, well that's all very well and good. We were able to get a complete description of geometric series because they are so regular and well behaved, and there's this very simple relationship between one element of the series and the next one. But what about, so we're asking ourselves this question, what about series that are nearly geometric? nearly and eventually geometric. So they're not exactly geometric, but maybe they act like ones that might act like a geometric series. Can we draw, so first of all we have to say, well, what exactly do we mean by being like a geometric series, or nearly a geometric series, or eventually a geometric series? To make that a bit more concrete. And what we'd like to be able to do is, if we can articulate that well, then hopefully we can, using the very well understood convergence properties of a geometric series, maybe we can also draw conclusions about the convergent status of these series. So what about these series that are nearly geometric, ones that might act like a geometric series? Hopefully we can draw conclusions about their convergence in a similar way. So what's the idea? Well, the idea is articulated in the ratio test. And what the ratio test does is we consider a series which is the sum of AM we'll suppose it's positive terms. So just adding together positive quantities. And then what we're going to do is we're going to attempt to evaluate the limit of AM plus 1 over AM. So we're going to take our series. If we've got a nice description for the terms in the series, we can divide the m plus 1 term by the previous term, AM. Suppose that this is a convergent sequence and its limit is equal to L, then what the ratio test will say is if, well, it's going to be greater than or equal to 0, but if it's strictly less than 1, then the series converges. If L is strictly bigger than 1, the conclusion is going to be that the series diverges. If L is equal to 1, then this theorem doesn't know. The limit comes out as exactly 1, we won't be able to draw any conclusion. It might be a convergent series, it might be a divergent. We may never know, or we may have to use one of the other tests to decide what it is. So this is what the ratio test is. Now what link has it got to do? What has it got to do with the ratio test? Well, a quick and dirty explanation, or quick and just a very rough and imprecise, hardly call it a proof, but a very rough sketch, the proof. If the limit of AM plus 1 over AM is equal to L, then what you can say is eventually the ratio AM plus 1 over AM is approximately L. It's not too bad, this sketch of the argument. I mean, there's nothing incorrect about it. It's not particularly detailed. We'll give a detailed proof of it shortly. So i.e. am plus 1 is going to be approximately L times am, eventually. Okay? It may not be at the start, but if this ratio is tending to the limit L, eventually it's going to be pretty close to L. No matter what epsilon distance around L you ask for, you wait around long enough, there'll be a point after which all the ratios are within that distance of L. So if you wait around, eventually you'll see it get pretty close to L, but then am plus 1 will be approximately L times am. So the series eventually behaves like a geometric series, eventually like, this is where the imprecision and the need for careful proof is, because these are kind of vague terms. But eventually it's behaving like a geometric series with R equals L. Okay? Because you see down here, when we just sketched ourselves the reminder of the geometric series just a few moments ago, we said when you divide, so xn was exactly a geometric series. When you divided xn plus 1 by xn, you always got this same number r. So here, when we're examining a series where the limit of the ratio is equal to L, eventually the ratio is approximately L. It's approximately always equal to L for any n beyond a certain point, eventually. So eventually, our element will be approximately L times the previous element. So that's, I mean, if this was an equal sign, it would be exactly a geometric series. It's not an equal sign, it's an approximately equal sign. So the reasoning is, because it's eventually behaving like a geometric series with R equals L, then just morally, because it's acting like a geometric series, it should have the same convergence properties. Morally, or just it seems reasonable, sum of am should have the same convergence properties. Same convergence properties as the geometric series. With R equals L, i.e. if L is between 0 and 1, implies convergence, and if L is strictly greater than 1, implies divergence. Now for the geometric series, if L was 1, we had divergence. But because that L equals 1 is the borderline between convergence and divergence, and we're only talking about the series we're examining eventually behaving approximately like a geometric series, because L equals 1 is the exact dividing line between divergent behavior and convergent behavior, if we just know that our thing is acting approximately like the ratio series with the geometric series with R equals 1, we won't be able to draw the conclusion, because we will only know the approximate nature of the series we're investigating. And if I know something is approximately near the border, I shouldn't say for definite, you can't say for definite which side of the borderline it is. If I know it's approximately near some interior point, I can probably say it's safely within that country or whatever, or that interval or that region. But if it's approximately near the boundary and I don't have any more precise information, who knows which side of the boundary it is, if it's convergent or divergent. Okay? Then it's too close to call, so to speak. Too close to call without any further information. Okay, so that's the rough sketch of the proof. It's not incorrect. It does have the main idea in it. It's persuasive and it's good, but it's deficient because it relies on words like eventually, behaving like this thing, morally, whatever that means. So it needs tightening up. It needs being made rigorous so that we can have data. Okay? We shouldn't go building our mathematics on such approximate arguments, even though in retrospect they'll be seen to be correct arguments. But there's many instances where people present equally persuasive arguments for results which eventually turn out to be false. There are a lot of conjectures floating around all the time in advanced research mathematics of things people suspect to be true. Very often they're backed up with kind of reasonable arguments of this kind of nature. But when people get around to checking all the details, oftentimes they turn out not to be true. And we discover new things by proving things aren't true as well. As well as discovering new things that are true. Okay, so let's look at the detailed proof. Now it's in the notes. I'll explain it for the convergence case, the convergent case, the L less than 1 case. And the L bigger than 1 case is fairly similar. Okay. Okay, let's go. So we assume is a series of positive terms, as it was in the statement of the theorem. And we assume that the limit of am plus 1 over am exists. It's equal to L, and it's in the convergent range. It's in the range that's supposed to be convergent. So we assume all this. So our goal now is to prove that this series is convergent. Okay? Rigorously. And we're going to compare it to, using one of our comparison tests, we're going to compare it to a geometric series that we know converges. Okay. Now, a little sketch will be appropriate here. I know L is to the right of 0. Okay, L could be exactly 0, but in general, I know it's some number, some positive number, and it's less than 1. Okay, so L is between 0 and 1. And I know my ratios are converging to it. And I want to see, I'm going to apply the comparison test, the standard comparison test. So I want to produce an inequality for my terms. I want to show that they're less than something, and I'm going to be comparing it to a geometric series, which will have r equals 1, or the common ratio equal to 1. So I want to make sure that these ratios are definitely less than 1 and away from 1. Okay? So I choose an epsilon value for my sequence convergence result. This is sequence convergence here. 1 minus L over 2. So I'm choosing epsilon here to be equal to 1 minus L over 2, which is half the distance between L and 1. Okay? L is less than 1, so 1 minus L is that remaining distance between L and 1. So if I halve it, then I know I have a nice interval, which is all of the numbers in the interval are strictly less than 1. Okay. Now there exists, so by convergence of this sequence to L, there exists an n such that Saeed got you using his predicates, the exists and for all predicates, maybe. So the backwards E means exists. Let's just stick with the English for a moment. Such that for all m bigger than or equal to m, I know that the distance from am plus 1 over am L is strictly less than this epsilon value. Okay, that's true because the ratios of convergence to L. Well, that implies that the am plus 1 divided by am is strictly less than, well, what is this actual value here? This actual value is L plus 1 over 2. Remember, if you add L plus 1 minus L over 2, you get L plus 1 over 2. So L plus 1 over 2 is actually the position of the right edge of that interval there. L plus half the distance between L and 1 gives you L plus 1 over 2. So that implies that AM plus 1 is strictly less than L plus 1 over 2 times AM. Now the key thing about this number L plus 1 over 2, L plus 1 over 2 is, I know, is strictly less than 1. L is strictly less than 1. So L plus 1 over 2 is strictly less than 1. And this is my link to, from this now I get my link to geometric series. Okay. This inequality here is true for every little m beyond capital M. So also, I know that AM plus 2 will be strictly less than L plus 1 over 2 times AM plus 1. Okay, that's just looking at the next value. Sorry, no. Sorry. So this inequality here is true for every little m bigger than or equal to capital M. So in particular, it's true for when little m is capital M. So here's AM plus a capital M plus 1 being strictly less than L plus 1 over 2 times a capital M. And also, when you look at the next value, you get a capital M plus 2 being strictly less than L plus 1 over 2 times a capital M plus 1. But when you combine that with the inequality you just have, you can say that this is less than L plus 1 over 2 all squared times a capital M. So AM plus 1 is strictly less than L plus 1 over 2 times a capital M. AM plus 2 is strictly less than the square of this number times AM. Also, when you look at AM plus 3, that's going to be strictly less than L plus 1 over 2 times a capital M plus 2. But when you combine that with the previous inequality, we get strictly less than L plus 1 over 2 cubed times AM. So you can see the pattern. This pattern continues. A capital M plus J is always strictly less than L plus 1 over 2 to the power J times a capital M. And this is true for every J bigger than or equal to 1. That's where we start. These terms here on the right-hand side, these are the terms of a geometric series. Okay. There's one fixed initial term, AN. And then each term is generated by just raising the power on the L plus 1 over 2. So each next term here is generated by multiplying the previous one by L plus 1 over 2 to the power J. The sum L plus 1 over 2 to the power J times a capital M. So that's a capital M. And this going from 1 to infinity, this is a convergent geometric series. It is a geometric series, but exactly the right form. Remember, the a capital M is just some fixed constant there. for this series. Each term in the series is just generated by raising the exponent of this number. So this is like the A in the geometric series, this is like the R, and it's raised to the R. So it is a geometric series, and it's definitely convergent as L plus 1 over 2 is strictly less than 1. And we know geometric series with common ratios strictly less than 1 are convergent. But then we've got this comparison, which is saying that our terms, remember, all our terms from our series are positive. They never become negative. So we've said that all these terms for every j, they're always less than these ones. These are the terms of a convergent series. So by the standard comparison test, our terms are even smaller than these, so they're even better behaved than the convergent ones. So our terms form a convergent series as well. So we can say by the standard comparison test, the sum from j equals 1 to infinity of a capital M plus j is also convergent. Okay, so we're using as well as the ratio test, we're making use of the standard comparison test. Well, what is this? This series is a tail of our original series that we're investigating. I.e., the original series, A little m now, where little m goes from 1 to infinity, has a convergent tail. Remember I talked about tails yesterday? From some point on in the series, the infinite tail of terms forms a convergent series. So therefore the original series is convergent as well. Because the sum of this series is just the partial sum up to am plus the infinite tail. So this proves the convergent case of the ratio test. The divergent case is proved. The divergent case follows a similar argument. Except this time, the comparison we make is comparing to a divergent geometric series. One where the common ratio, it won't be exactly L plus 1 over 2, it'll be some other number. Maybe it will be, there will be L plus 1 over 2 again. But there the quantity L plus 1 over 2 will be strictly bigger than 1. And so this thing you're looking at will be a divergent geometric series. And the inequality comparison we will have here will be the terms in our series will be strictly bigger than the terms from the known geometric series. So see the printed notes for that. And the L equals 1 case, well, once you've seen those two arguments and you think about the L equals 1 case, here's L, which is equal to 1. And if I know my ratios A plus 1 over M are converging to L, well, I can put as small an interval around L as I want. All I know from the convergence is that the ratios are somewhere in here. So I don't know whether they're bigger than 1 or less than 1. They might be either. They might be hopping around and changing from being bigger than 1 and less than 1. So I can't isolate, I can't say for definite whether they're less than a geometric series with L strictly less than 1, or whether they're greater than a geometric series with L strictly bigger than 1. All I can say is they're close to a geometric series with L equals 1, but that's the one that's right on the borderline between convergent and divergent behavior. So basically, I know my ratio is close to 1, but without any other information, with just purely that information, I don't know to which side of 1 it is. So we can't, just with this information alone, we can't establish a comparison, the right kind of comparison, a good comparison between our series, the sum of AM, and a known geometric series. Geometric series with known convergent or divergent. I could say that they're strictly less than a divergent geometric series, but that's the wrong kind of comparison. If you know you're better behaved than something bad, you could still be bad or good yourself. I can also say they're bigger than the terms of a convergent series, but that's like saying you behave worse than someone really good, but you could still be good or bad in that case. It's the wrong kind of comparison. Whereas here we compared, we said our terms behave better than terms that behave good, so our terms are good as well, so our terms are produce a convergent series. So, yeah, this good, bad behavior way of thinking can be hopefully strong. Let's show an example of it working. Geometric series test. The ratio test. So let's jump in, let's look at question 8a from page 25. I'll take any questions about the proof in a moment, or I'll ask for questions if there's things you want to check up on. But let's look at an example. Question 8a from the end of chapter exercises, which is this series here. Two over n factorial. So is this convergent or not? Okay. Now, if you try and apply the ratio test, you're taking the ratio between consecutive terms, and you're attempting to find the limit and deciding whether the limit is bigger than or less than 1. So the series that the ratio test is likely to be able to give you a conclusion about are ones where when you do form that ratio, they somehow simplify, or the ratio behaves nicely. So here we see the presence of a factorial. And that is helpful, because when you divide one factorial by a neighboring factorial, all but one of the factors are going to cancel. Okay? Remember, n factorial is n multiplied by n minus 1 by n minus 2, multiplied by every integer down to 3 by 2 by 1. So when you put two neighboring factorials and divide one by the other, all the factors cancel except for one remaining. Okay? So to apply the ratio test, we take the n plus 1th element, which is 2 over n plus 1 factorial, and we divide it by the nth element, which is dividing by 2 over n factorial. And just to get our fractions straightened out, that's dividing by a fraction is the same as multiplying by its reciprocal. Okay, that looks messy and complicated, but it's also going to simplify a lot. The 2's are going to cancel. All of the factors in the top factorial are contained in the bottom factorial. They're all going to cancel out, leaving just 1 over n plus 1, leaving just n plus 1 in the denominator. Okay? Everything else cancels out. That limit we can decide on immediately, because it's a reciprocal 1 over something, and the denominator is getting larger and larger without any upper bounds. The whole thing is converging to 0. So this is our L in the ratio test. Okay, so it's definitely strictly less than 1. best it can be. Okay? So the ratio test then says that the sum 2 over n factorial converges. It doesn't tell us what the value is. Of course, we can approximate the value of the limit by just looking at ever longer partial sums of this. Just look at the longer and longer partial sums, you'll get better and better approximations of the limit. The partial sums will be an increasing sequence bounded above by the limit. So they'll be increasing and getting closer and closer to the limit. So you can watch the evolution of the partial sums, and the kind of behavior you'll notice is, they'll be getting closer and closer to the limit. We know exactly this, well, we can calculate the step size each time. It's 2 over n factorial. So when you see those numbers becoming small, then you know you're within that, you're fairly close to the limit. Let's maybe look. Let's look at an example where it's, I think, inconclusive. Yeah. We could try applying the ratio test to the harmonic series. Okay, everybody loves the harmonic series. We already know it's divergent. We saw that from the integral test. We also saw that from our grouping argument, which we gave the very first lecture on series. We could try the ratio test on this. So you take the limit as n goes to infinity of the n plus 1th term of the harmonic series, which is 1 over n plus 1, divided by the nth term. The nth term is 1 over n. So if you're dividing by 1 over n, you're multiplying by n over 1. So that's the limit of n over n plus 1. And if you do, that is a convergent sequence. You do your trick of dividing above and below by the highest power of n. See, it's 1 over 1 plus 1 over n. We can apply our algebra of limits results about sequences to this, and this has the limit 1. Okay, so unfortunately, the ratio test can't say anything either way about the harmonic series. Okay, as far as the ratio test is concerned, it might be convergent, it might be divergent. Okay? I mean, it maybe gives a conclusion in the sense that it says, well, you're very close to the border between convergent and divergent behavior, but we can't say exactly where you are. That's what the ratio test says about the harmonic series. No definite conclusion about its convergence or divergence. Okay, is that okay? Any questions about the proof that we laid out there? It's a nice example. It's a nice example to see towards the end of series because it ties together quite a number of things. The convergence of sequences. Made use of the idea of convergence of sequences. We made use of the comparison test, setting up inequalities. And the comparison series we knew about its nature because of the geometric series test. So it ties together many of our previous results and uses them to very good effect. It gives us a situation where we can now draw conclusions about series which we probably couldn't have drawn conclusions about up to now without the aid of that test. Okay. Now, we are nearly finished this chapter, I would say. There's just huge amount of time. Yeah, so there's some other interesting series examples I'd like to show you. These relate to the questions 13 to 16 on the tutorial handout. So this is about telescoping behavior in the partial sums of a series. And I'll have time to do one of these briefly. So we'll consider the series, which is the sum of 1 over n into n plus 1. Now, this compares to the sum of 1 over n squared, and so is convergent. Okay, the dominant behavior of the denominator is the n squared term, so it's going to act similar to, by the limit comparison test, it's going to have the same convergent status as the sum of 1 over n squared, and that's convergent. But we can actually calculate a precise value for the sum. For the infinite sum here. Using what's called the partial fraction expansion of the term 1 over n times n plus 1. Now, we'll be encountering partial fraction expansions are important. Fortunately, I don't have time to go through full explanation now, but if you look at page 35 of the notes, it's a good explanation on pages 35 through the 37 of those. And you may have seen them used before in various places. You may have seen them in your previous study. We will be coming back to them. We will say more about them. But the partial fraction expansion of this term is 1 over n minus 1 over n plus 1. If you add together these two fractions or subtract them, using the rules for subtracting fractions, you'll find that they come to exactly 1 over n times n plus 1. Now, finding partial fraction expansions, there's a method through which we can go to find the correct coefficients on each of these simpler fractions that you have in a linear combination here to make up the starting fraction. That's described on pages 35 through 37. But if we consider the partial sum, let's call it Sk. So Sk is the sum from n equals 1 up to k of 1 over n times n plus 1. Well, when we change the representation and instead use 1 over n minus 1 over n plus 1, you see, what you get is, when n equals 1, you get 1 minus a half. When n is 2, you get a half minus a third. When n is 3, you get a third minus a quarter. And this pattern keeps going until when n is, let's say, when n is k minus 1, you get 1 over k minus 1 minus 1 over k. And when n is equal to k, finally, you get plus 1 over k minus 1 over k plus 1. Now normally a big long sum of up and down fractions would cause you problems. You wouldn't be able to, it'd be hard to evaluate. But of course, not in this case, because you see very nice behavior here is each negative term is cancelled immediately by the following positive term. Negative 1 over k cancelled by the 1 over k. Okay. Notice each negative fraction cancelled by the following positive one. Okay. So that just leaves two remaining things. The first positive term, which had no preceding negative fraction, and the last negative one, which has no following positive fraction, because it comes at the end. So that means the partial sum is extremely, well, it's quite simple. We've got this really nice expression for the partial sum. This is the partial sum sk. So the infinite sum, which by definition is the limit of the sequence of partial sums. Remember, that's the definition of the sum of an infinite series. The limit of the sequence of partial sums. But our partial sums here are very well behaved. We've got very clean, simple expression for them. 1 minus 1 over k plus 1. And we can tell immediately that that is a convergent sequence, and indeed we know its precise value has precise value 1. It's the 1 over k plus 1 bit is converging to 0. So this is one of the nice cases where we can actually say precisely what the sum of the infinite series is. All of these convergence tests we've been looking at in sections 2.5, with the exception of the geometric series test, they all just give you an output of its convergent or its divergent. They don't tell you the precise value. But here is an example where the structure of the series is such that we can actually say we can get an exact expression for the partial sums, and so we can say precisely what the value is. And other series, like the ones in questions 13, 14, and 15, they can be tackled in a similar way. Okay? But if you're unfamiliar with it, you will need to read the material on partial fractions, which is on pages 35 through 37. So we will be looking at that in more detail later on in the course. Okay? So we'll leave it there for this morning.